Hi, so the topic of my talk today is computational and theoretical fluid mechanics approach for modeling transport into dense tumors. This introductory slide is on the fluid mechanics modeling of tumor transport. Let's look at the current state of art over here, the hypothesis that can generate new understanding, and the main goals that we would like to pursue. In terms of the state of art, computational fluid dynamics of CFD simulations can only generate data on a case-by-case basis. So if we want to use fluid mechanics as a diagnostic tool or as a drug delivery tracker, as of now, it is not very feasible, especially because of the time constraints to reconstruct a tumor geometry from medical scans and then running the simulations and post-processing the data. So often we see in literature the use of mean continuum transport frameworks like the Darcy's law for permeable membranes and the Stirling model for semi-permeable membranes. But these two techniques, they date back to the 1850s and 1890s respectively. And that brings us to the two main hypothesis points. Number one, if we can integrate numerical computations with sophisticated theoretical modeling, we should be able to cover a wide range of tumor microenvironments. And number two, this resulting theoretical computational framework should be able to generate data against that wide parameter space of tumor geometry features, which may include the packing fraction inside the tumor stroma or the curvature of the blood vessels in the tumor microenvironment. And working along those hypothesis items, the research in my group could be classified into the following overarching goals, which essentially resonate with the specific aims that I'm going to cover in a few minutes as well. So number one, we need to generate tumor geometries that are both idealized and medical imaging best. Number two, we need to be able to computationally replicate the realistic rheology of blood transport in the tumor vasculature. Number three, we will develop numerical and theoretical models for intratumoral fluid mechanics. And number four, we will compare the model data with experiments, first to benchmark the modeling assumptions and then to figure out how to fine-tune the modeling framework to make it even more realistic. Now, in this talk, I would first cover the work that we have done until now, and this also comprises the preliminary data that I'm including on my next level of the proposal, which is the junior investigator project. Now, as the first goal, we have built a biomimetic tumor stroma with a straight adjoining blood vessel. The arrangement of the fiber bundles in the extracellular matrix, or ECM, was based on volumetric reconstruction of CT images. In the second goal, we have simulated blood flow and then plasma perfusion through a fenestra opening. Note here that a single-phase, steady-state simulation of blood cannot resolve the hemodynamic information necessary to quantify the spatial dynamics of the suspended particulate matters in blood. So the model that we have implemented had to be multiphase and pulsatile. In the third component, we have analyzed a CT scan from a mice tumor that was shared to us by the North Dakota State University Animal Core, and we tested it for its suitability to reconstruction for future CFD simulations. Okay, so until now, this gives a brief summary of what we have done. I'll spend the next few minutes discussing some of the details of the work done before I go into the specific aims and the goals for the future junior investigator proposal. So let me first go over the biomimetic architecture. We conceptualized a 3D idealized model and then took a 2D cross-section through it. The idea was to replicate the essential fluid dynamic properties in a simple domain. This is what the 2D model looks like. We have tested three different fenestra opening diameters, namely 0.1, 0.3, and 0.5 micron. Initially, we faced some computational issues. The multiphase domain in the blood vessel comprised the red blood cells, or RBCs, the white blood cells, or WBCs, and the plasma, and we detected that some RBCs are entering the fenestra. But that cannot be the case, as the RBCs at 7 to 8 microns are larger than the fenestra opening. So we modified our approach to a two-step simulation. We first modeled a three-phase transport in the blood vessel and measured the volume flux of plasma entering this very small groove that leads to the fenestra opening into the tumor. In the second step of the simulation, the same plasma volume flux was tracked through the ECM region, which is over here. Before we go into the details of this two-step simulation process, let me also note that the bio-inspired geometry that we see here was structured based on the typical packing fraction in tumor scans. And this packing fraction is also a function of the solid stress that these tumors are under. So in this particular test case, the packing fraction of the fiber bundles was 0.27. In comparison, the average packing fraction was 0.30 in this CT-generated image from a real tumor. In the first step of the simulation, as I already mentioned, the fluid domain was multi-phase. We considered three phases: RBCs, WBCs, and plasma. To replicate a realistic rheology, the flow was pulsatile as per the cardiac cycles. The pulse consideration is also critical in terms of the biology of the problem, as the time period of 0.735 seconds is enough to impact diffusive transport into the tumor, which in turn can affect hypoxia. Here we show the simulation snapshots in the blood vessel at different time steps. Although the mean transport might look alike, you can see that the wall-induced effects do cause some spatiotemporal fluctuations near the fenestra opening, which is over here, here, and here. But things look more nuanced as we track the dynamics of plasma inside the stroma. To remind you, Model 1 has a 0.1 micron opening fenestra, Model 2 has a 0.3 micron fenestra, and Model 2 has a 0.3 micron fenestra, and Model 3 has a 0.5 micron fenestra. We see that while the plasma perfusion is proportional to the opening size, which is expected, the rate of perfusion slows down as time progresses or as the diffusion length scale increases. For a quantitative analysis, we have resolved the color scheme and have obtained the ratio of the red plus green zones to the blue zone. We have then computed the exponential scales that would relate the color differentials to the opening diameter ratio. So here X is the scale between the models 1 and 2, and Y is the scale between models 1 and 3. The ratio X over Y flattens over time, implying that the rate of diffusion is decreasing with increase in diffusion distance. This also crucially agrees with the Fick's law, where the rate of diffusion R is inversely proportional to the diffusion distance D. So we can consider this to be a zero-level validation of the simulation approach. Finally, as a third wing of the accomplished work, we have processed a real tumor scan and have developed a stereolithography file, which can then be used as a numerical simulation space. Before I go into the outline of the future work, please note that our current findings have been presented as a poster last year at the American Physical Society's Division of Fluid Dynamics annual meeting. We have also uploaded a manuscript on bioRxiv for the work done. The paper was submitted at Experimental and Computational Multiphase Flow in June. We got the reviews back last month. It's a recommendation to publish with minor revisions, and we plan to get the revisions in a couple of weeks. Okay, so let's now move on to the elements of the Junior Investigator Project, which is the future proposal that I'm going to discuss from here on. There are some obvious improvements that we need to incorporate into our modeling framework. The two main ones are, number one, we need to be able to simulate the electrohydrodynamic effects from the negatively charged glycocalyx patches along the luminal surface of the endothelial cells. And number two, we need to model the transport process with more realistic wall curvatures for the blood vessels, as that can often impact the flow quite drastically. Well, the rationale for these improvements is obvious. They would make our modeling approach more realistic, of course, but I also want to identify and establish the novelty of our work. After a thorough literature review, I think fluid mechanicians like us can right now contribute to the following two major aspects. Number one, the non-Newtonian rheology of blood has not been modeled well yet. For example, the plasma in tumor vasculature contains some high viscosity regions and some low viscosity regions. And it is a low viscosity domain that actually undergoes extravasation into the tumor. Number two, while many groups have done CFD and have done CFD simulations of transport in this kind of systems, and have also used mean transport models like the Darcy's law and the Stirling model, not many have tried to develop a rigorous theoretical model yet. A model that can build off the numerical inputs and can also be validated experimentally. So let me call such a model a diffusive reverse advective or DRA model. The model will track the dynamics of platelets or other solutes penetrating the ECM. The diffusion here is because of the inward force owing to the concentration gradient, and the reverse advection results from the outward force owing to the elevated interstitial pressure. So with that backdrop, I have structured the future project around three specific aims. Let's first go into aim one. Here we will develop a more realistic model for transport inside the blood vessel. Number one, the walls will be A, sinusoidally curved, and or B, the local wall curvatures will be extracted from the image scans. Overall, we plan to generate a wide range of wall curvatures for around 10 to 12 vessel geometries. Now, number two, the fluidic domain will have four phases: RBC, WBC, high viscosity plasma, and low viscosity plasma. The low viscosity plasma has been shown to diffuse into the tumor, which is more akin to if I may say, a reverse jamming behavior. In number three, we will simulate the electrohydrodynamic effects by including the discrete anionic patches along the vessel wall, which stand in for the glycocalyx patches in a real blood vessel. And number four, the simulated data will be post-processed to extract the plasma volume fraction perfusing into the tumor through the endothelial gaps and the fenestra openings. So platelets that move through gaps like this and through the fenestra openings like this. Now let's look at aim two. So aim two will build around modeling the fluid mechanics inside the stroma. It will first involve numerically simulating the movement of plasma inside the stroma and also embedded solutes. And the geometries would be both idealized and CD-derived domains. Next, we will develop a theoretical model with inputs coming from our numerical simulations. As I mentioned before, our work aspires to go beyond the typically implemented mean transport loss, but this also constitutes the most high-risk part of the project. We will invoke a convection diffusion equation where the boundary conditions on the local concentrations at the inlet to the tumor stroma and near the necrotic core will be fed from the numerical simulations. The numerical constraint for no slip along the fiber surfaces will incorporate the packing fraction consideration of the setup. Also note that the sink term here will be due to the lymphatic transport, for which I can gather some estimates from my collaborators here at SDSU. Finally, these PDAs will be analytically solved on Wolfram Mathematica with the boundary conditions and the packing fraction effects. So this approach should be able to generate a penetration trend as a function of the ECM packing fraction and blood vessel geometric properties. As a future vision, we should be able to estimate the penetration just based on the packing fraction without running any high-end CFD simulations. The third aim is on validating the theoretical numerical approach and designing appropriate experiments to that end. The first experimental concept involves a 2D microfluidic mimicry of the simplest numerical setup with the opposing forces replicated through a hydraulic pressure head and a magnetic field. I do admit that this system is of course far removed from a tumor microenvironment, but the simple setup will serve for basic physical benchmarking of the mathematical convection diffusion approach. I pitched the experiment idea to my collaborator, Dr. Anupam Pandey at Syracuse University. SDSU plans to extend some matching support for Dr. Pandey to run this experiment there. I expect that the difference in the physical transport and the theoretical predictions will help us to fine-tune the nature of the boundary conditions, which I had described over here, and fine-tune them such that they are closer to what we might come across in a real physical system. And with those appropriate corrections, we go to the next level of experimental testing. This would involve a more realistic validation of our modeling approach. For this, I will collaborate with Dr. Joshua Reineck at the SDSU College of Pharmacy. He's working on 3D culture cell models and can provide us with a tumor structure wherein we can simulate the transport process. Dr. Reineck can also decellularize the ECM and make it more similar to the CFD system. The subsequent comparison of the penetration trends will provide any further corrections that we might need on the boundary conditions in the theoretical numerical model. Next, we will compare the revised CFD data with the experimental penetration trends in an untempered tumor spheroid. The differences will provide us with estimates on if we need to include any underlying medium in the ECM space to mimic the interfiber constituents that we come across in a real tumor stroma. Okay, so I hope this gives a good account of where we are headed to. The ideas should align with a future large-scale NSF proposal. And in terms of the team that I'm proposing, Dr. Reineke will provide internal mentorship on this project at SDSU, and he will also be one of the main collaborators. Dr. Luke Thogarajan at UC Santa Barbara would be serving as the external mentor on this project.